Okay, in this video, I'm just going to go through the vacuum chamber design for the project I'm working on. It's like a big portion of my thesis. So I'm a grad student studying physics, and this is like an entirely new project with an entirely new. Um, it's like from the ground up. So we don't even have like a lab yet. So everything is being built new. So a lot of my like main first project was just to design the vacuum system. Um, so I'm in a trapped ion research group. So in order to trap ions, we need a good vacuum. Um, so I'm just gonna design or go through the design considerations, and then basically explain we arrived at how I arrived at a specific design. I'm not going to go through a bunch of like pressure simulations or anything. It's going to just be like mechanical almost. Um, so yeah, this is the main vacuum chamber right here. So this is an optical table. The table is 5 feet by 10 feet, so it's pretty big. It's recessed. I'll get to that later, but that gives you some idea of how big this thing is. It's mainly made out of titanium, and for that, there's a couple of reasons. One is the weight. So this is a relatively large vacuum chamber for trapped ion research groups, and the weight, with something with titanium, will weigh a lot less. So it'll probably be less than 200 pounds. So it's a big reason for choosing that. Whereas if we made this all out of stainless steel, like most groups would, it would be like 300 or more pounds. So that was one major reason. Another major reason is titanium has a lot lower outgassing rate. Now that may or may not be the limiting factor in your base pressure, depending on your vacuum design, but the lower outgassing rate is a huge plus, and it also allows us to bake our titanium at a lot lower temperatures. So you don't have to do pre-baking with titanium. You do need to create a thick oxide layer, and the people that are manufacturing the custom design I made are doing that for us. So if you pre-bake at a high temperature, you actually might destroy that oxide layer, and that layer is what prevents outgassing at ultra high vacuum. So that can be pretty thick. I think like microns, maybe 8-10 microns. So if you destroy that, you might lose a lot of the benefit you have from titanium. So we're only going to bake it at like 150. So yeah, those are the two reasons why most of it is titanium. Now, titanium's a lot more expensive, but it's well justified in this project, especially since it's going to be an open access experiment, so other people can hope, in like years, people will be able to log on. Other researchers or experimentalist groups will be able to remotely run experiments on this system related to quantum information research. So, or just atomic ammo physics experiments also. But so that's the reason why it's okay to spend a little more. Anyways, custom designs, when you're really paying for that, like when you get a custom vacuum chamber, you're kind of just paying for the NRE and the engineer's times to make those drawings, do all the tolerancing correct, weld everything, titanium. Some of it has to be welded under like argon or like inert gases. So you're just paying them for their time. It'd probably be, I don't know, maybe 10 to 15% less if you went with stainless steel, but it's because it's a custom design is why it costs so much more. But again, with this kind of project, it's it's well justified. The system needs to be consistent. It needs to be a good base pressure. Otherwise, we'll have to reload the trap all the time. And we want it to be room temperature because cryogenic systems just even more overhead than room temperature vacuum systems. And it requires a little bit of expertise, and you have to have good maintenance with it. There's also vibrations that come with that, which are not ideal for ion traps, but they can be dealt with to some degree. It just takes more time and engineering costs to do something that's cryogenic, like 4 Kelvin. So we want room temperature, titanium. That's the main design. Really, the whole vacuum chamber is kind of built around the optics. So that's kind of where we started. So I'm not going to go into why we have all these lasers, but optical access. So these are all viewports on the side here. There's a viewport here, but it's not pictured. It's suppressed. And this chamber is the trap down here, and this would be sitting upside down, basically. So the trap would be facing the optical table. So the most important design, some of the most important things in trap ion experiments is the optical axis. The more optical axis you have, the more orientations of beams you can run. Generally, the more different kinds of experiments you can run. I mean, there are kind of preset orientations that you want with most like ion trap experiments, but the more flexibility you have, the better. So the optical axis was by far and away the most important aspect of the vacuum system. In particular, some of the optical axis that's most important is the Ramen reentrance. So to drive gates in ion traps, you can use microwaves, but most people use Ramen transitions. And if you want to drive individual gates on maybe a chain of ions, you need to actually physically focus light onto specific ions that you want to entangle. If you're using Ramen transitions and you just globally address with both your Ramen beams, then you're going to be entangling all your ions, which is not what you want to do for most experiments. So to be able to focus down onto a specific, like one ion in a chain of, let's say 17, and not hit your neighbor ion, you're going to need to focus down to like 3 microns or less of beam waste. So in this experiment, the ions are about 4 microns. And the tighter you can focus, the less crosstalk you'll have with the other ion, higher fidelities you'll have. So to focus down to 3 microns or more, you need to expand your beam quite a bit. So the numerical aperture of this Ramen reentrant, so I call it a reentrant viewport because it's like in the vacuum system, right? So is estimated, including the objective, so there's objectives sitting in here that are doing the final focusing, is estimated at about 0.37. So we really can't get higher with this experiment using normal reentrant windows, because if we do, so the reentrant window constrains the size of the objective, which constrains the clear aperture, and that clear aperture is kind of what your estimated NA is. So if we make our reentrant any bigger, to make our objective bigger, we're going to start clipping these beams here, and these are fundamental beams for cooling, detection, loading. We need them, and we need them in this orientation. So we cannot make it any bigger. The only way I see that you could do better with individual dressing, with optical fields, is to either have optics integrated in the trap. So you'll send some fiber or some collimated beam into some grating that's fabricated into the trap, a waveguide, whether it's laser written or planar, that will focus at the ion. Our trap is made at Sandia National Laboratories. It's like the most sophisticated ion trap you can kind of get. It's free for us to use as long as we use it for experimental purposes. Fabricating something like that is very hard to do, so there's no way we can change the trap. So we can't really improve our individual addressing scheme, and thus our like 2 cubic gate fidelities that way. And then another way you could possibly increase your NA is just by having actual in vacuum objectives. So now that your objective now can take up the whole area that your ramen reentrant would normally take up, but that's more expensive because you need to be able to move the objective in vacuum, and those kinds of piezo stages are pretty expensive. The ones that can go to ultra vacuum, and it's kind of just like a little bit better, right, than just using a reentrant. So it's not like it's not a huge leap forward. So overall, we ended up staying with the classical reentrants. You'll notice here that this is exposed glass. This is like a titanium appearance in Inventor, but this part is actually glass. So that allows us to get a little bit higher NA, where this is usually capped with some metal piece here, which would be clipping our loading beam. So the Ramen lasers are like the most important in the experiment if you want to do quantum operations, and it's highly dependent how much optical access you have is really important for your individual addressing. And basically, our design is kind of all around this one major consideration. So I kind of just worked my way backwards from this constraint. So we have basically the maximum Ramen NA we can get with classical reentrant type approach. That's limited by our 45-degree beams. Specifically, it's limited by our loading beam, which is 50 degrees. It's off axis, 5 degrees, because their loading and our like cooling and measurement beams need to spatially separate because they're the same frequency, and our polarization is important, so there's no other way to separate them unless we spatially separate them. So that's the main constraint. Other than that, this is a really high, this is CF60 flange, that's a high NA. This is CF40, this is a high NA. That's important because we have these beams that need to spatially separate. There's 10 ports on this experimental chamber from Kimball Physics, right? It's also titanium. 8 of them are for a laser axis or like optical axis. So this top part again is not pictured, but it's for imaging. So we'll have another objective in there. And it's going to be a reentrant, so it will drop down close to this shield. And the 2 other ports that are not optical are the electrical, which is here, and then obviously you need a port to pump on, right? So the decision to put the electrical port in the actual chamber was made basically because it's a shorter distance than if we would try to like wire these things like a foot or more. So our trap needs more than 100 independent DC voltages sent to it. So if we try to wire those a far distance, that would be rather difficult. And what we chose to actually to make the connection between the trap, which is basically like a chip that's inserted into a zero insertion force socket, which is then soldered to a flexible printed circuit, which is then push pinned onto the feed through. The material that the FPC is made out of is really high outgassing rate. It's really bad. It's bad for vacuum. You can bake it a lot, but it's really bad. So putting electrical feed through close makes that shorter, gives us better vacuum. The flexible printed circuit has advantages because you can. It's a low. It has it allows you to put more ground planes, which would potentially reduce crosstalk between these voltages, but it also makes the assembly process a lot easier. So that's what we're using for our primary connection. We'll look at that right now really quick. So this is the flexible printed circuit. Just change the view. Okay, so this is a flexible printed circuit. It's one piece. I'm not specifically designing it. I had to work with Rich, the person designing it, because I'm designing a vacuum system, so there needs to be back and forth. It's one piece. These are the pins on the ZIF socket. This is the ZIF socket. These are the push pins on this side, which will push onto the micro, our custom feed through, which is micro sub D connector. So each pin has a 0.05 inch pitch. And that's nice because then we can take this thing on and off of the feed through, and we can clean this whole thing separately because there's going to be a lot of solder and flux on there, and that needs to be cleaned really, really well for ultra vacuum. So the fact that it's detachable is a huge plus. The last vacuum system I worked on, helped build, was not detachable, and it makes it a lot more difficult. So that was a big plus. I'm not going to go through all the different lasers. Most of them are continuous wave CW lasers, except for the Ramens, and then these three ones are ablation lasers. So ablation lasers are what we use to load the trap. We have some substrate with like barium on it, but it's barium chloride, and we hit it with a laser, and it sublimates, and then all kinds of things come off, but that cloud eventually can make its way to the trapping region. And then this cable is an RF cable. Again, that's like what Rich is working on. So to trap ions, you need some kind of RF. You can't trap it with ions with just DC voltages. So yeah, the shield will be grounded, and also provides mechanical supports for our ablation targets. So these targets are meant to pivot in two directions. These are through holes, so it can pivot up top, and this can pivot down below. There's still some more work that probably needs to be done with these, and the alignment needs to be tested. So we'll have to put this in an oven and cycle it up to 20 degrees Celsius or up 200 degrees Celsius a couple times, and then see how well the alignment stays in place. But those are the internals. Everything else is just to help support this so that it's connected to the main chamber. So yeah, the whole system here is designed around basically the optics, the optical axis, and then all the pumps and everything else was kind of secondary, but they're still very important. So a lot of these are just support structures. There's three main portions of the vacuum system. There's the experimental chamber down here. These are magnetic field coils. The experimental chamber we just looked at, we saw the internals, we saw the reentrance. This is the pump chamber. This is a 5-way cross if you look here. And then there's another titanium nipple that houses 3 types of pumps. And then up top this is actually stainless steel. And this has all the diagnostic equipment. So all the gauges, an RGA, a leak valve. Then you need a bake valve so that you can connect it to a turbo pump and a roughing pump and get down to, some decent pressure, like 10 to the -6 millibar or something. Basically get to high vacuum so that your ion pump can work well, and you don't use it, at something really low, and either destroy it or decrease its lifetime. So when I was going through this design, I still kept in mind the vacuum system, and I liked pumping on this port because has a huge diameter compared to most ports. This is a CF 150, so the internal diameter is like 150 millimeters, and it's a lot larger than what most people pump on. Most people pump on like a CF60 at most, or most ion trapping. They try to pump on something like the CF40, but this huge conductance will help us get to a lot lower pressure. So if we look at this chamber itself, it's going to be low pressure chamber, but the highest gas load by far is in the experimental chamber. That's because of the complicated trap. It has some epoxies, and then the FPC, the flexible printed circuit, it is a Pyrolux AP, so it's like Kapton rolled with copper. It has a very high outgassing rate. There's also PEEK material, which may or may not be switched out, but PEEK is a plastic developed by NASA, and that's a very high outgassing rate. So the gas load in this area is a lot higher than anywhere else in the chamber. So the large conductance, which is over 1,000 liters per second, is going to help alleviate that higher gas load, and it increases our effective pumping speed by a lot. So we can look at the pump chamber here. This is like a drawing or a cutout. So this is the experimental chamber down here. This is the pump chamber, the 5-way cross. The ion pump is on the back side. It's not pictured. And then this diagnostic chamber. So this high conductance allows us to put NEG, which are non-evaporable getters, very close to the trap. And that's good because placing things close and line of sight is going to increase your effective pumping speed by a lot. So non-evaporable getters are good for ultra-high vacuum because they have high rates of pumping for hydrogen, and hydrogen is one of the most prevalent at ultra-high vacuum in terms of just the background gases. There's methane, there's also argon, there's carbon monoxide, there's some nitrogen, but hydrogen is by far some of your limiting factors at ultra-high vacuum, so using NEGs that have really high pumping speeds for hydrogen is important. Another advantage of the NEGs is that we can put them line of sight. So we have a titanium sublimation pump. It's 3-filament. It has an ambient sputter shield, but you can't put a titanium sublimation pump on line of sight, obviously, because you'll just start sublimating and coating whatever can see the filament in titanium, and that will just destroy your experiment. So the NEGs have a distinct advantage at ultra-high vacuum in the sense that you can put them closer in line of sight than TSPs. In general, if you have a room temperature system and you want to go to ultra-high vacuum and stay there, you're going to need an NEG or a TSP. They're getter. I mean, the ions are getter pumps too, but they're a lot better for getting hydrogen, which will be your limiting factor. We also have to have an ion pump because NEGs and TSPs won't pump certain types of gases. So NEGs are titanium, aluminum, vanadium, zirconium alloy. That's the specific model. I don't think they all have zirconium, but and it's really porous, and it either phys absorbs or chem absorbs items that come into contact with it. So like molecules will land on the surface, and a lot of the times that'll happen for a sustained period before it becomes saturated, and then you'll need to reactivate it. So the surface and NEGs will become entirely coated, and then you'll have to run them at high temperature to drive all of the stuff on the outside into the bulk of the material. And then you'll have a fresh coat. It also sprays hydrogen, all kind of crap all around your chamber, but you have to do that. Generally, these things don't become saturated like at ultra high vacuum for like years or more, probably. TSPs, I know, you don't continually run them, but you can run them at ultra high vacuum for a very long time. So same with ion pumps. Anything that's 10 to the minus 11 millibar, 10 to the minus 12, or even 10 to the minus 10 is going to have, all of these pumps are going to have really long lifetimes. So yeah, titanium, when you have a fresh coat of titanium, it tends to bond more to like titanium oxide. And then once that coat is used up, you have to spray a new coat, right? So there's no bulk material there. It's not like the NEGs. You can get thin film NEGs. You can even coat thin film NEGs on chamber walls and stuff like that. It's hard to do with things that are varying diameter. So like this complicated Kimball chamber right here, it would be very hard to coat that evenly. And if you coat too much, you're going to flake. So you don't want huge, like 10 micron thick flakes of NEG coming off in your experiment. So a lot of the times it's just a few microns or 1 micron, and they use it for like large like accelerators, like huge beam lines, stuff like that. But you can even coat small tiny pipes. I saw a thesis that did that. But yeah, so we didn't use any NEG thin films. We just have the nice oxide layer from the titanium, but there was just too much of a risk. So the TSP, while it won't really change the base pressure in this system based on mole flow simulations. It's there as more of like a safety, just in case something goes wrong. Like most people, when they're designing systems, won't put TSPs and NEGs in the same system. It's understandable. But the perceived issue with that is, one, usually you don't need them. If you have one, you're usually fine. It's going to be extra costs. It's probably not going to get you lower base pressure to put in another pump somewhere else. And two, there's a risk that if you fire this, if one thing is activated, like our NEGs are activated, we've ran it at 60 watts or whatever, we got it up to 550 C is what we need to get it up to. And then if there's a fresh coat on there ready to be absorbed, and we activate our TSP filaments, the TSP filaments could saturate the NEGs. So when the TSPs are activated or the NEGs are activated, you have a whole bunch of crap coming off of it, and it's temporarily increasing the pressure, and it's possible that could saturate. I've never worked on the system with both, and most people don't, but it's there in an event that the NEGs somehow fail, then we have something that, whether it's a connection or we can't reactivate it well or something, we have something, the TSP, that could actually use that that could keep us at low pressure without the NEGs. So it's a factor of 2 or 3 higher base pressure in my simulations using the TSPs, but it's still ultra high vacuum. Good ultra high vacuum if we can bake everything properly. So it's more of a safety measure. And again, with this project, you normally wouldn't do something like this on a normal experimental project in a lab as a grad student, but this is supposed to be like an open access resource, and everything needs to be just like a little more scrutinized. If other researchers are going to take the experiment seriously and stuff, we need to have pretty serious designs in place. So normally you wouldn't do this, but because of the nature of the project, how integrated it is, and what the end goal is, it'd be nice not to have to spend months trying to get something back online, because sometimes it can take that long to get a vacuum system back up and running. So having this backup is nice. And then, there's the ion pump here. It's 75 liters per second, so it's even smaller port than what could be put on there. And again, that's kind of a weight thing. So it's like 40 pounds. If we put on a 150 liter per second or something, it would increase the weight quite a bit, like by another 40 pounds. And because we'll be in ultra high vacuum, the main pump will be the getters. And this is simply just to deal with the argon and the methane and other non-gitterable gases, which like 90% or more of the gases at ultra vacuum are gitterable. So it's really not such a, to decrease the conductance and the effective pumping speed a little bit to get us 40 pounds, it is worth it. It really shouldn't have an impact on our base pressure. It's a star cell, so it does have lower pumping speeds for nitrogen. It has similar pumping speeds for hydrogen as standard diodes, but it has higher pumping speeds for like methane. So that's kind of why we went with that. Was the methane. Okay, so the Diagnostic Assembly, this is all stainless steel. The reason for that is the thermal expansion coefficient of titanium is like half that of stainless steel. So I'm trying, on this whole system, I've been trying to reduce the amount of stainless to titanium connections there are, just because I don't want something to go wrong when we're baking it, where we develop a leak, and then especially during the final bake, and then we have to do a whole bunch of things. So the trap really can only be baked once, or you got to get another one. So we really can't have any failures in that respect. So on this chamber, there's 4 stainless to titanium connections. There's this TSP, ambient sputter shield. So the ambient sputter shield is to stop it from sputtering all the way down the chamber, and also to just increase surface area, so you have more titanium coated, and you can pump more. So yeah, this is one. Titanium stainless steel. The electrical connection down here is also titanium to stainless steel. The Kimball chamber is titanium. The electrical custom feed-through is stainless steel. And then up here is titanium stainless, and the ion pump has a stainless steel flange. So there's a couple ways to deal with varying thermal expansion coefficients in vacuum system. So a lot of people won't bake very high, so you go up like maybe 150 or 200 degrees Celsius maximum. What you want to do generally is use titanium bolts for all of these, because they have lower thermal expansion coefficients. You can slightly bake them so that when you start to cool down, then you tighten them, and this is like a partial pre-bake that's just dealing with matching these thermal expansion coefficients. So generally what I've heard is if you bring it up to 150, and this is just like a dry run, you bring everything up to 150C, and then you bring it back down, and you tighten while you're going down. When you go back up and come down again, when you cycle it again, you're not gonna have issues. So that's one way to deal with it. And then another way is some people there's one manufacturer I've found that makes bimetal flanges. So it's Atlas Technologies. It's in Washington. They got really cool stuff, but we didn't end up getting our chamber from them, but they have really cool products. So what they do to make the bimetal flanges is that they work with aluminum, they work with copper, they work with titanium and stainless steel. I don't know what bimetal flanges they have exactly. I know they have stainless steel and titanium. And then they have a copper layer in between them to help match the thermal expansion coefficients. And the way they do that is they like literally take these plates out into like a mine, and they use TNT to smash them together. So we didn't get those. Those are expensive. But that would for sure solve your thermal expansion coefficient issues. I've talked to enough people where I don't think it's going to be an issue to do the titanium and stainless steel matings. People do it. So that's and the reason this is stainless steel up here is because it's so far from the trap that I'd rather have less titanium stainless steel connections um, rather than have a whole nother expensive titanium gimbal chamber that would be slightly lower outgassing rate. So it just didn't make sense. So yeah, this is stainless, definitely has no impact on the outgassing rate or on the base pressure. Okay, we can talk about a little bit what's up there. So I've gone over the pumps. Here's the diagnostic chamber. So the RGA is kind of pictured. You can't really see it, but so there are where did I go? So there are two gauges. One is there's actually like 4 gauges in total if you're counting them. So the RGA's got a Prani gauge. It just shuts off the RGA if you get too high pressure. But we got a cold cathode Prani full range gauge. Cold cathode gauge we just did because it's a little less accurate than the hot cathode gauges, but it's has no hot filament, which was something I was concerned about for a little bit until I moved all the diagnostic stuff really far away. But it's got no hot filament. It's really just supposed to be used as like an order of magnitude, like estimation of where we are. It's not really very accurate. It's plus or minus 30%. Hot cathode gauges at ultra high vacuum are plus. Hot cathode gauges in general are plus or minus 15%. At ultra high vacuum, all these things go to crap in terms of the accuracy. But then we have an extractor gauge, which is kind of like a hot cathode gauge. It's very similar, except the collection filament is shielded slightly, and it reduces the amount of errors, and it makes it more sensitive than normal hot cathode gauges. So that can go down to like 1 E minus 13 millibar. So that's why that's on there, because we want to be able to measure more accurately at ultra high vacuum. Yeah, then the all metal bake valve is standard. You have to have that. The all metal leak valve is, we don't have specific plans for that, but if we needed to backfill the system with inert gas or something, we could do that. Some people use these to create a flow of argon past their trap where they have like an RF coil, and it makes a low energy argon plasma that cleans the trap. We can't really do that. We don't have a way to create the flow, and we don't have an RF coil, so we can't do that. But the leak rate on there is pretty low, and I don't expect that to be a limiting factor at all. It's a variable valve, so it's not like a CF thing, but so is the all metal bake valve. And then we have the coupling for the NEG thermal couple, which lets us activate the NEGs. And then there's a viewport, which is, again, kind of an arbitrary choice. Lets you look down the back of the chamber. I know it might be useful to see something. So these are the diagnostics. Yeah, again, the main choice, which is just try to get high conductance to them. So there's relatively high conductance. It's straight. It's not like zeroed off in a corner, but it's also far from the experimental chamber because you don't want any of those filaments messing with the experiment at all. The RGA is also there to periodically run scans and just maybe every month or something see what the background pressure is like, and then maybe get more information in case of a failure, help you diagnose better if it's a leak or not. And it's just to get more information about the system. It's got a really hot filament that we're going to need to pre-bake, or a really large filament we're going to need to pre-bake, and it's hot when it runs. So we'll have to deal with that separately in the bring up phase, but it can give us useful information. Okay, so yeah, that's basically the design. Hopefully we'll get into the mid minus 12 millibar range Really depends on how well we bake all of the internals and heat treat everything. Um, you can bake things at 150 for like a day, or you can bake it at 200 degrees Celsius for like 2 weeks. You're going to get a lot better results with that. But so depends on how far you want to take it. This thing hasn't been built yet. All of the parts have been ordered. Um, Everything is actually in our lab, but because of the coronavirus, we haven't been back in months. This frame is, here we talk a little bit about, this frame is actually connected with welded tabs here. So I thought I would make those just because you can make the frame a lot smaller than what people typically normally have. And then this will allow us to easily mount the system so that we have more room underneath the chamber, which is important again for the optics. So if you'll notice here, we have all these optical components. They're not at the right height level yet, but providing room under the chamber will let us maybe put 2 levels of optics if we need. So the frame, the smaller frame, lets us bring this up a little higher, and it lets us still mount the system well and provide more room. So the welds, generally these welds in the vacuum system are fragile. They can just be like interior welds, like welded only like on one side. So I made the frame so basically all the forces there's like no shear forces, so it's like pressing up on into the welds. So and again, the chamber's actually not that heavy, but you don't want to take any chances with ripping things off. Yeah, so the vacuum chamber is pretty closely coupled to the optical design, and that's where I started first, was making sure we can get all the beams in, get a high NA for our Ramen reentrance. And then, yeah, besides that, we can also look at how well it couples to the optical design, and gives us an idea of how big of an optical table we need. So this is to scale, and these are just different optical components. So this is the vacuum chamber. So making layouts like this helped me ensure that we have enough room to fit everything in our optical designs near the vacuum chamber. So it also kind of validates all of the vacuum designs, validates all the optical access in the vacuum, besides just, the beams blindly going in. We can now say, okay, we have this beam going in. We now have these piezo mirror mounts in these stages. This is how we can get full control of this beam, and we can make the shapes of the beams that we need at the trap with these specific components. So making this mechanical layout here, while it just is, making this mechanical layout helps us a lot, because it validates with actual components that we have all the degrees of freedom on the beams that we want being sent to the trap, and that there are no major redesigns need to take place because we now can't fit something. So there's a couple of ways you can approach large scale systems like this, but going through and making different schematics, whether it's actual CAD designs, or it's these 2D schematics, or it's like make a lot of optical schematics for these that just has a bunch of optical information, kind of can help you tease out your design before it's totally complete. Obviously, you're going to learn a lot when you start to build it, but this gave me a good sense that everything will be able to be, all the optical components will be able to be controlled remotely, and that it's consistent with Rich, who's doing all the control designs, and that we at least have a rough idea of where to start. So that's the system where it's at now. We're still kind of waiting on to get back in because of COVID, so we could start building the vacuum system. I think the first thing I'm going to do is optical designs that I've made, but I'll maybe put ZMax videos or something in a different up at a different time. But yeah, so that's kind of how we got to this vacuum chamber design. It's about as much information as I have about it. It started with the optical design. Vacuum was kind of secondary, but it's kind of this back and forth that you have to play when you're going through the design process of seeing, okay, is that going to work or is that not going to work? And, you start to assign values to certain attributes of the system, and that can help you make informed decisions when, you have to give up something or in lieu of something else. So yeah, hopefully this will be built soon or relatively soon. We'll have to see. The table itself is also custom. So we have a whole cavity here that we want to install, and that's for all the imaging optics. And that increases the width of the table because most standard tables are 12 inches, but this is now 24. We can't go with a standard table that's 12 inches thick because the width of the cavity is 12 inches. So we have to increase that width and increase the center of mass on these legs. And when that happens, if the center of mass is too high above the optical table legs, then you can get some like rocking motions when you're trying to elevate the table. So because of the high center of mass of the chamber and a bunch of lead wall that's not shown here because we're using barium-133, it's radioactive, so we need to shield it. And the cavity, we're like right on the edge of what would be stable and what would possibly be, only maybe stable. So to alleviate that concern, it made sense to have Newport draw up these custom table design. And when these legs are recessed into the table quite a bit, then it lowers the center of mass a lot back into where it would be stable for sure. Yeah, so that's basically it. I think I've gone through most of the design. There's not much more I could say about the vacuum system itself, so I think maybe next time I'll just do something with the optics.